So I thought that it would be appropriate for me to start the thermodynamics part of my list of videos talking about the most interesting topic in thermodynamics that I care about or that I like, which is actually the second law. So the second law is the strange thing that everybody talks about. Maybe you can go to other YouTube channels and see what they say. And most of them, I think, they are chemists and physicists talking about molecules inside a box or disorder and that kind of stuff. But we as engineers, we would like to know another approach. Okay, so what entropy? Oh, so the second law is the statement of a that defines a property, and that property is called entropy. So let's just see little by little what we mean by that. So it's a lot of things, okay? I mean, it's just one thing, but it's a lot of things to different people in different fields of study. But so far, let me just start. Let me just make some sense about the idea of entropy with some easy example nowadays example. So let's just go with this one. Let me just see if I can do this. Okay, so let's just got ourselves a tank. Okay, whoop, the lid is open, so you can pour into that. I'm gonna pour something which is, oh, let me just use this format just because I want to yeah, about this one. So you fill with gasoline. Okay, so this thing is filled up with gas. I mean, not filled, but something, some of it, and then the other part it needs to have air. Oops, air plus gasoline. Okay, so you have that, and then just to dramatic effects, you need to throw. You need to throw. What am I trying to do? Okay, I'm trying to do this. You need to throw something in. What? Well, let's just call it a catalyst. Oh, a catalyst. What fancy word to talk about a match. So you light a match and put it in. Okay, so this is the flame of the match. You put it in and you close the lid as fast as you can. So the time is not important here, but imagine that you are trying to do that. So this tank has some properties. Oh yeah, really? Yeah, it has some properties. What was one of them? Well, one of them is that it's isolated. So I don't know if you know from your courses what isolated means. It can mean several things. Most of the time, it means that it's thermally isolated. So that means that you are not allowing the transfer of heat. But let's just say here what I was trying to do is to change color. I wasn't too successful with that. So you close the lid. Something is happening inside the tank, which is called combustion, okay? But there you have it. This is your state one. So this is your system, this is wording about thermodynamics. So this is your system. And let's just think that the tank is isolated, okay? So this thing is isolated. Isolated means that there is no transfer at all, at all. Transfer of what? Of nothing. There is no transfer. Anything can go in, cannot go in, and anything can go out. So if there is a nuclear explosion inside the tank, you won't hear it. You won't see the tank shake a bit because no information can escape the system whatsoever. So by information, I mean you cannot hear the sound of what is happening inside there. You don't feel the heat. You don't feel the expansion of the shock wave that is taking place into that, or whatever you want to think about it in a very dramatic phenomenon, which is a nuclear explosion. But let's just call it that you don't feel anything. Okay, why? Because this thing is isolated. Nothing gets in and nothing gets out. What do you mean by nothing? Well, no mass can go in, so no mass, no energy. But I think you remember energy can be transported in two ways, heat and work, but none of them can go in or out because it's isolated. What else? Well, this guy has nothing to do with thermodynamics, but nonetheless, let me just put a momentum. There are transfer of momentum, but here in thermodynamics, we actually don't study too much. Now, let me just go with, I don't know, electrical charge or something like that. You cannot transfer electrical charge uh, through these boundaries because this thing is isolated. So electrical charge. This also is not a very thermodynamic thing to talk about, but nonetheless, it could be. Okay, so no electrical charge. What else? Well, no entropy. Oh, but we haven't defined that. Yeah, I know that. But the idea is that you cannot know anything what's going on in there. You don't know any of its manifestations, what's going on in there. So what is that? This is just plain simple stupid, right? Well, it's an idea of an example. Okay, now let's just go to two. What do you think you will see when you open the lid if a simple combustion process happen inside there? Well, what you will see, maybe you will see that you will have, well, let me just do it this way. Nope, I want it this other way. You will see this there. I was just putting like that. That thing over there is just smoke. You will see, actually, plain and simple, in plain word, this thing is just smoke. Oh, is that entropy? No. So what the hell this guy has to do with entropy? Well, something, but let me just go there. So what you will have over here is that you have smoke. What is that? Well, actually, these are, oops, I don't want to be like that. So what you have over here is maybe CO2. It depends on the combustion, but you have gases. You will have gases, and you will have water vapor. Maybe you will have, if this thing was too hot, if the combustion was too hot, maybe you have noxes over there. Oh, maybe it was not a very good combustion process, so you have carbon monoxide, and you will have all that stuff. Okay, and maybe some well, let me just see, volatile organic compounds, or whatever the stuff you study about engines or heat engines. You will see something about combustion, and these are typical products of these processes. Okay, so yeah, but what are you doing this? Well, I'm actually doing this to show you something. Okay, well, what you see over there is smoke. See, now here comes the question. Try to put this one, air and gas, try to put that in your car. Okay, so this is your car, and I'm gonna ask you a question. Does your car move if you put air plus gas? Well, yeah, actually, you need to put air plus gas in order for this thing called car to move. Otherwise, it doesn't move. Fine. Okay, so you're right. So I need to put air plus gasoline in order to move the car. Fine, I already know that. How much does the car goes on if you put air plus gas? Well, actually, it depends on the car, on the size of the tank, of the gas tank, or whatever you want to call it. But let's just say it gives you 100 kilometers. Okay, so let's just say you can move around 100 kilometers before you need another take of air plus gas. Fine. And then what? Well, how about if you just put, instead of the air plus the gas, because they are kind of expensive, the air is not, but the gas it is. So what about, instead of that, why don't you just pour smoke into the tank? What, smoke? Yeah, why don't you just put, this guy was working with air plus gas. Now let's just put with smoke. With smoke, I just mean these gases, okay? These production, combustion products gases. So you will put it over there. So how much do you think this thing will move? I think, I'm just saying, okay, in order to put something, it just will drive around 10 meters, shaking a little bit or a little bit more. It will shake for about 10 meters, and then the engine will die. Okay, that's what I will think it will happen. So, and you will say, well, that's obvious because, and I would say, what do you mean it's obvious? Hey, look, this thing is isolated, right? So can you do the first law? Yeah, I can do the first law. I think I remember the first law for a closed system. This thing is a closed system. Why is this guy a closed system? Because it was isolated. So no mass, yes, so no mass. So that's actually the definition of a closed system. Therefore, you will have that delta U equals to Q plus W. Maybe you don't need to know too much of this. I haven't give you any numerical data, but nonetheless, you know that this thing cannot happen, okay, because it's isolated. This thing cannot happen because, again, it's isolated. Then you will know that delta U equals to 0, okay? Okay, if you say so, yeah, I say so. Therefore, it also means that U2 equals to U1. That is, the energy before is the energy after the process. Oh, okay, so fine. So the first law gets you here, and you will say, okay, now I'm asking you, if these two tanks, okay, one and two, these two different moments have the same energy, why cannot you drive your car 100 kilometers as it was the case in one? Why cannot you drive it around 100 kilometers too with the same energy? Okay, so that's a nice question. What the hell is happening over here? It seems that something has changed from one to two, but not the energy. Something happened to the energy? No, nothing happened to the energy. The energy is the same one. I mean, this is a little tricky of an example, okay? This is not actually completely true because some of heat is actually escaping from the car, okay? A lot of heat, I would say, is escaping from the car. That's why you have a radiator and you have a water system, a cooling system there in order to put out heat from the engine. Okay, but nonetheless, let me just go with the original idea. So you have one state one that gives you what you want, moves you around 100 kilometers, and the other stage has the same energy, but it seems that it cannot produce the same amount of work. So that's the whole idea of this thing. What the hell is happening to the energy? And the first law, it says, I don't have a clue, buddy. So the first law is telling you, I really don't know what the hell has happened. I can tell you that the energy before is the same thing as the energy after that one. Okay, so there must be something else in the world or in the universe that doesn't allow me to move around the car more, or at least the same thing as I had with what I have at one, with what I have at two. Something changed. Something from the system actually changed. That thing, guys, is the entropy. Okay, so just for the sake of fun, let me just try to, this is not a definition, okay? It's just a description. Entropy is a measurement of the dispersion of energy. Okay, so yeah, I know it doesn't say a lot, okay, but something seemed to has happened here, which is, okay, something here was really compact, okay? There was something in the chemical arrangement of the fuel over here, the gasoline, that allowed you to do something very useful, which was to move the car, okay? And something here is not arranged in the same way. Yeah, I was criticizing the general approach of using molecules, but it's another way to picture it. There's something here that is more dispersed. It's not as ordered as it was here. So we are not going to go into the microscope, micrometer world, or nanometer, or whatever you want to call it. But what you have, the effects that you feel over here is that you cannot drive around the car the same distance. So first thing, I don't know if you know this, but what they told me back in high school, or I don't know, maybe elementary school, they told me, look, buddy, energy is the ability to do work. And if I see the second law, I know that this thing, it's bullshit, okay? This thing needs to be bullshit over here. Why? Well, because I have the same amount of energy here, U1 equals to U2, and they don't do the same work. Okay, how is that possible? Well, okay, so I know this is a bit of a stretch of an example, but it's to give you the some physical sense of what entropy is. There has something to do with the entropy that we haven't know something about, but this thing over here, this thing has an entropy called S1 and an entropy called S2, and something happened to these guys. What? Which one goes up or down? We don't know yet about that. But the thing is that there was something lost in this process. Something was lost, at least the ability to actually the ability to do work. Okay, so this is an important part of the second law. That is why we need a second law. Okay, because the first law is a good, useful tool. It tells you, look, buddy, something in the universe is going to be constant no matter what. Oh, so mass. Well, there's something else which is called energy. Oh, okay. So yeah, I know a lot of this type of laws which are like conservation laws. Okay, there are a lot of those in the physical sciences, like 11, for example, or 10 or something like that. They all write themselves with an equal. So this equal means that there's going to be a balance from this side to this other side. But then it comes the second law, at least a mathematical expression of the second law due to Clausius, Rudolf Clausius. And he said, look, delta of a property that we don't know too much about it, but let me just call entropy. He called it entropy as a negative energy or a non-useful part of energy, as a dissociation or disgregation of something. So delta S should be equal at some point, but most of the times higher than Q divided by T. That's it. Is that it? Yeah. And this thing has enormous consequences. First of all, this is really weird to look in science. What? This thing over here. We have something like that in quantum mechanics too. Um, that has to do with Heisenberg, okay? But so far, this is another thing which is really weird. There's something bigger, yeah, all the time. Well, not all the time. There, at some point, there can be equal, but most of the times, or some of the times, this delta of this property is going to be higher. What do you mean by Q? Well, Q is a heat. What do you mean by T? Well, T is the temperature. So those things are things that maybe you can actually grasp. Okay, so let me just joke around this thing. So this thing is like, this little play. Imagine a playground where children are actually playing, and this thing is a balanced stuff. So, mm, so, so there, yeah. Imagine that this thing is a playground for kids, and this thing is a seesaw. Okay, so most of the times delta S is this way because it's higher, has more weight than this little kid, which is called Q divided by T. Okay, or this thing is actually something called entropy transfer. Entropy transfer. Okay, so more things to know. Okay, and most of them is like this. Imagine that we want to make a mathematical trick because we don't want to deal with these inequalities. Inequalities are really hard to, well, they are really hard to work with, okay? Maybe you know, but if you put an equal in a graph, you will see something like this, or maybe this, or maybe this. But these things are uh, curves, okay? But if you put inequalities, if you work with inequalities, you're actually working with regions. So maybe you're talking about this region, or maybe you're talking about this region, or something like that, because inequalities, they talk to you about areas, okay? So, okay, that was just the one type of justification or to work with with an equal. So if I want an equal and this guy is heavier than this guy, maybe what I can do is, okay, so I'm gonna call delta of that property called entropy. It's gonna be equal to the entropy transfer, Q divided by T, plus one more kid. Okay, so let's just put one more kid over here, and this guy is gonna be equal to S gen. This guy is the beeline of the universe going to thermal dead, okay, going to equilibrium, because this guy is something really unknown. There was something wrong. It seems like a trick. It seemed like a mathematical trick in order to dispose of this inequality and to work with an equal, okay? But this thing is called entropy generation. This thing is called entropy generation. For the guys that like theory about thermodynamics, this, well, it's not a lot of theory, but this thing is a property. It characterizes a system. This thing over here, it's a transfer, it's an interaction of what? Of entropy. And this thing is neither. This thing is something that just comes up and decides that the air plus the gas, okay, just becomes smoke. And just by that combustion process, this guy S-Gen appears and says, okay, so instead of moving your car 100 kilometers, you're gonna move it 10 meters. So this is the big deal about it. This is the second law for closed systems, plus S-Gen, okay? And this has some important things, important consequences, okay? Let me just write for open systems. This is for closed systems, okay? Let me just put it for open system, ds dt, which is the change of the level of entropy inside a system in time, okay? So that's the rate lost or gain of entropy in time by the system. It's gonna be equal to the mass of flow dragging around its entropy, the entropy of that substance, minus the ones that the mass flows that are going out of the system, okay, dragging around its own entropies, plus this. Actually, it should be maybe there are a lot of heat interactions there, so you're going to have a lot of entropy interaction between the system and the surroundings, plus S gen. Okay, let me just do some housekeeping over here, and that's it. Later, in another video, I will talk about what the hell is entropy generation. Nobody actually knows how it works, but something happens in nature that at some point you cannot use the same amount of energy to do a thing all over again, and to do a thing all over again, and to do a thing all over again. Something is lost in the way, and it's not energy. It's not energy. It's actually the ability to do work. You lose that when you're doing a process. Okay, so this guy over here has to do that. This is the quantification of how much work or ability to do work you will lose in a process. Okay, well, enough for today. I know that it's a little bit tough to talk about this, but let's see you later, guys.